So as we wrapped up at the end there, starting to write down the Hamiltonians for actually how this qubit interacts with this cavity. And I want to do it, as I said, at the simple two-level system description level, where I'm not going to worry about the higher states of the transmon. So we have a spin 1/2 for the qubit. The cavity is a harmonic oscillator, and then this is the interaction term. This is the general version. It's called the Rabi model, but most of the time this is going to be approximated with a slightly simpler version. And so this product has 4 terms in it, and we're going to throw 2 of them away and just leave this one, sigma plus A, sigma minus A dagger. And so these are the 2 sort of intuitive terms where you swap an excitation between the qubit and the cavity. You excite the cavity and de-excite the qubit, or you de-excite the cavity and excite the qubit. The full model actually has double creation and double annihilation terms. They are not an error, they are physical. It's a sort of counterintuitive thing, but for purposes of today, we're just going to use this simpler version, and this one is called the Jaynes-Cummings model. Okay, and so then H total is, of course, the sum of these, HQ plus HC plus HQC. Okay, and the regime of operation of essentially all of these devices is what's called the dispersive regime. And so this is going to be where omega C minus omega Q is much, much larger than G. And so this is the realm of non-degenerate perturbation theory, where you can think of the qubit as mostly being qubit-like, the cavity as mostly being cavity-like, and then you can treat this term using second-order perturbation theory. And in the dispersive regime, H total looks approximately like this. So 1/2 H bar omega Q sigma Z plus H bar omega C A dagger A. And then the key term that we acquire looks like this. So H bar chi sigma Z A dagger A. And so this is the effective dispersive interaction. This is, I think, a fairly weird looking term if you haven't spent some time contemplating it. It's the product of a photon number operator and a qubit sigma Z. And so I find that it's much more useful to rewrite this in the following way. So that our total Hamiltonian is 1/2 H bar omega Q sigma Z, otherwise known as a qubit, plus H bar omega C plus chi sigma Z A dagger A. And so I want to think about this as an effective frequency for the cavity. And this is rather an abusive notation because I've just added a number and an operator. But this is the correct way to think about this. And so what do I mean that this is the effective frequency of the cavity? So for me, the most intuitive way to do this is to look at a couple of examples. Okay. And so let's imagine that the qubit is in its 0 state. Just going to take that as a given. Well, so sigma z acting on 0 is 1 times 0. And so that means that omega c plus chi sigma z is just omega c plus chi. And so our total Hamiltonian is essentially 1/2 h bar omega q plus h bar omega c plus chi a dagger a. And so the cavity frequency went up, assuming chi is positive. So we've added chi to the cavity frequency. And now we can imagine the opposite case where the qubit is in the 1 state. Okay. Sigma z on 1 is -1 times 1. And that implies omega c plus chi sigma z is omega c minus chi. I apologize for these two relations. I did not set this convention. I don't like it. It's very annoying, but it is very, very common in quantum computing. I think you can blame it on the positive G factor of the nucleus from the old NMR days. But for me, this is always confusing. That 1 is the -1 eigenstate of sigma z and 0 is the 1 eigenstate of sigma z. There's something sort of wrong with that. If anyone wants to know where that came from, I'm happy to discuss it afterward, but it's a complaint and aside that's probably not really relevant here. But it means that the total Hamiltonian is now minus h bar over 2 omega q plus h bar omega c minus chi a dagger a. And so that the cavity frequency decreased. And so we can actually use this to get a readout of the qubit. And of course, I just erased my diagram. So let's put it back. And so now let's go back to thinking about our coplanar waveguide resonator. We have ground plane, center pin, and now I'm going to really explicitly add these two ports. And so this part is a resonator, and this is a piece of coax. And so this is going to go to the output, and the input comes in here. And we put the qubit in. And so now with these two ports, we can start to imagine an experiment where I send a microwave tone in this side, and I measure what comes out that side, and I try to use that with these shifts to determine the qubit frequency. And so what am I going to see? So if I look as a function of drive frequency, this is a harmonic oscillator. It has a well-defined frequency. And so if there's no qubit in the cavity, it died a tragic death during fabrication somewhere and it didn't make it, then I'm going to see a nice resonant peak here at omega c. But if there's a qubit in the cavity and it's in the up state, then this is no longer the frequency at which the cavity exists. Instead, at omega c plus chi, there is a resonance assuming that we're in the excited state. And over here, at omega c minus chi, is a resonance, assuming the qubit is in the ground state. Okay. And so what's really important here is that the frequency of the cavity depends on qubit state. We know how to measure microwave transmission. And the third thing that's really important is that chi is big enough. So I've drawn this, the derivation that I've done so far is true for any value of chi, but I have drawn this with a relatively large chi, so that this resonator shifts over by a significant amount depending on the qubit state. And that's where the big values of G come in. And so in atomic QED, well, let's see. So chi is basically G squared over delta. Delta is omega Q minus omega C. And so it's the coupling strength squared divided by the frequency difference. And so if this is going to be big compared to the line width, I need a big enough G. And this is where the really big G that you get in the circuit QED implementation really helps you. You can't usually, you cannot get this kind of resolution in the atomic version. The G's aren't big enough. Oops, okay. And so what that means is that we can now use this microwave transmission to figure out the frequency of the qubit. All right, and so now the question is, how can we do this the most efficiently, right? So one option is we scan across the resonance and we find the peak. And if the peak is here, we declare it to be in 1. And if the peak is there, we declare it to be in 0. But that requires doing a scan. That's a lot of measurement. There's actually a much more efficient way to do this. It turns out we only need to look at one frequency. And so if I redraw this diagram with a little bit less clutter, so this is the resonance if the qubit is in the 1 state. And this is the resonance if the qubit is in the 0 state. So this is omega c minus chi. This is omega c plus chi. And so what I can do is I can measure transmission at this frequency, right? So if the qubit's in the ground state, I'm sitting on the peak, and I'm going to get maximum transmission. On the other hand, if the qubit is in the excited state, the peak is over there, and I'm now way off down on the shoulder. And so just by checking whether my transmission is low or high, I can figure out if the peak is here or not here. I don't actually know where it is, but that's the only information that I need if it's a two-level system. G or not G. And if it's not G, it's going to be the other. And so this is how we actually do these measurements. It's much, much, much faster than sweeping out the entire resonance. And this method is called dispersive readout. Yeah.
The readout is the large frequency. How do you have it and
Okay, so the question was, if the resonator is gigantic compared to the qubit, how do you have a device with a lot of qubits? You make it really, really big. is effectively the answer. There's a couple of tricks of the trade. And so one is that we never make a resonator in a straight line. We always tend to make them like this. Okay, this is somewhat helpful. It takes it from gigantic to huge. But there are also other ways to make a microwave resonator. This is sort of one of the earliest and the most common, but there are much more compact ways to do it. Signal routing is sometimes a little more annoying. It's kind of a pick your poison sort of question. But it is a serious worry with this device footprint. And when the semiconductor qubits and the superconducting qubits people get into pissing contests, then these are the kind of accusations that fly back and forth. Oh man, look at how big your device is, and no, you have 25 control lines. When we get drunk and fight, that's what happens. No, but the size of these devices, all kidding aside, is in fact a genuine concern. A lot of the problem is that we can't make parallel plate capacitors without them being super lossy. If we could do that, a lot of the stuff would be a lot smaller. Yeah.
Why is this person real? How can you use that for a long time?
So this regime, which I have erased, of detuning much larger than G is called the dispersive regime of cavity QED from way back when. Let's see, Andrew, do you know why the dispersive regime is called dispersive? Apparently it's a stumper question. I don't know why that's the word used for non-resonant in this case, but that is the traditional word for it. Probably for an effect that we never pay any attention to anymore. Yes.
Did the convention get flipped in the graph? Or was the one flipped? Is the one that's subtracting the side?
Yes. In my world, 0 is the ground state and 1 is the excited state, and the Hamiltonian is sigma z. And every once in a while, I belatedly try to put in enough minus signs to get back to the NMR convention. But I can just detune the qubit on the other side and make chi negative and fix all of my mistakes. Yes. No, there's far too many minus signs.
You have a question? Here you go. Looking at the Hamiltonian that you have erased, yeah, we can think of the other way around. Like here, state of the spin changes the
yes,
the wave,
yes, and
wavelength
so
of the photon.
yeah, so I grouped it this way. So 1/2 h bar omega q sigma z plus h bar omega c plus chi sigma z a dagger a, and you're absolutely right that I could have grouped it this way. So yes. I could have put the sigma z a dagger a in with the sigma z, and now I have a qubit whose frequency depends on the number of photons. This is called photon number splitting. It happens all the time in these devices. In certain styles of architecture, that splitting is actually used to do gates conditioned on the number of photons in the cavity and things like that.
But that doesn't alter the state of the qubit or the measurement outcome?
You can't. I think that
basically
you're right that the picture that I have put up is sort of incomplete to tell you that when you send microwaves through at this frequency, nothing goes wrong with the toy picture that I've told you, but nothing goes wrong with the toy picture that I've told you unless you start to drive it too hard. But it does mean that if there's light in the cavity while you're doing operations, it does weirdo things to your qubits.
Thanks.
There's another one in the back where I think we need a relay.
Ready?
So how big is this, let's say, spread of the resonance frequency of the modified resonance frequency compared to the line width? Or let's say, how well can you suppress if you shine in a microwave and you're in the wrong state? So how
That's
much
the next
transmission is
diagram
needed?
that's coming up on the board. Okay, and so as the question suggested, it's very important how big. Nobody's got hit on the head yet. How big that splitting is compared to the light width. And so you've clearly got sort of three cases. So the line width of this thing is traditionally denoted by kappa. And so this is an example where chi is quite a bit bigger than kappa. The shift is many line widths. You can also have something like this. So this is chi of order kappa. And so now the drop in transmission is only about a half in power, or you could have sorry, let me redraw this, make this guy fat. Okay. So this is chi quite a bit less than kappa. And so these are the three regimes. Another nice thing about superconducting circuits is, in fact, this is easy to achieve. The line widths are small enough and the couplings are large enough that you can get to this kind of a well-resolved splitting very, very easily. But it turns out actually that you don't want to, because this is a really big difference in transmission, but these cavities are relatively narrow. And so let me redraw this diagram in the middle here. And I want to have the same splitting, but I'm much better off having two fat things to get me to chi approximately kappa. So there's not as large of a difference in the signal, but because the line width is wider, the cavities respond faster. And so you actually get more signal out that way. This is the intuitive regime. This is the optimal regime. And it's very easy to select where you want to be. You can change the size of these coupling capacitors. If you want more line width, you just turn this into a big digitated capacitor. Starts to look like two interlocking castles, and then you can get a lot more coupling and things like that. And so it's actually very easy to control, and the native line widths are large enough that this is easy. And so it actually works really, really nicely. So that was all that I wanted to say about just sort of single qubits and readout and stuff like that. And so I wanted to stop and take any last few questions before I move on and start talking about how you can construct simulators from these kinds of things and what are the sort of unique tricks of the trade which are facilitated by the fact that these are quantum circuits as opposed to other implementations.
There you go.
Yep. So I just want to make sure. So when you're describing the readout, should I think of that I'm actually integrating a lot of photons? So is that case like you're actually really doing a projective measurement, or you're more like you're just measuring like an average of sigma z?
Yeah. And so what actually happens is that you send in a modest sized coherent state. I don't know, 3, 5, 10 photons, nothing huge, but not single photon. And then measuring the amplitude and phase of the coherent state coming out performs a projective sigma z measurement on the qubit. The longer you wait, the more you measure, the more sure you are that it's sigma z, that it's in that sigma z eigenstate. There's a couple over there. Nice
Thank you.
catch.
So I think you are mentioning like duration of the readout pause you are applying. So I'm actually thinking that if you are doing it like too short a pause, you have like other than just quantum mechanics, you also have like Fourier broadening of the pause frequency, and that could be also the issue that limits how long the pause is. And is it like some consideration you also have to pay attention to like how long the pause is, so you have a well-defined frequency of the pause?
So we're usually more worried about being able to do it as quickly as possible, so there's as little decay during the measurement pulse as possible. This particular interaction is QND, so if the qubit would behave, the longer you measure, the better of a measurement you would get. And so you could go long and slow and single frequency and everything's fine, but the darn qubit keeps trying to decay, and so you have to try to go as fast as you can. Lifetimes in these things are up to a few hundred microseconds or so, maybe a little bit longer than that, but they still decay. I think Yushin had a question.
Who wants to say? Oh, okay.
Can you shout?
I'll repeat the question.
So kind of directly going up to the like to make sure it doesn't decay, you want to measure as fast as possible. So in that case, like how often this measurement accurate is, like what happens to the qubit?
Okay, so the question was, what goes wrong when you try to measure as strong and as fast as possible to try to get it over with before there's a decay? To be entirely frank, I have avoided knowing such things. But like one of the things that happens is you can naively just start cranking up the drive power. You say, I would, you know, if you're limited by your detection SNR, you just want to get more signal amplitude through in a shorter amount of time, you crank up the drive power. And eventually when you do that, you start making transitions to unwanted states of the qubit. That if it was in 0 when you started, it might not be in 0 by the time you're done, just because you drove it so hard. You can saturate these qubits and you can completely blow them out of the water, actually. Like, it's a trick we use all the time to check if they're alive, actually, is to saturate them. Yeah.
This is a Dilfridge question.
Yep.
So, I guess when it comes to atomic and atomic systems, you kind of get ground state for free. Atoms are going to be in the ground state unless you excite them. For spin states, not for motional states, but it does connect to motional states because my question's about thermalization, and you know you do have your Dilfridge at say 100 millikelvin, but you might have a trajectory in which some point you are not at 100 millikelvin. Temperature is not really a well-defined idea for a single particle, right? So you might have thermalization of the qubit up to the higher states of your anharmonic oscillator.
So, I mean, I think that for these guys, the notion of temperature that's probably the most important is the radiation temperature. So the average occupation of microwave photons at the qubit frequency. And just because the thermistor on the bottom of your Dilfridge is reading 20 millikelvin doesn't mean that your radiation temperature actually is that. There is a long and painful fine art of filtering your lines just well enough to get good radiation temperatures. But if you're not doing a super careful job, then you will see a sort of residual one-state population even at the base of the fridge. And so that ends up making it like a little bit mixed. It's never perfectly pure. If you have a good setup with single shot fidelity readout, you could check the qubit state before you start and then use the measurement to clean up. But my group certainly doesn't do that.
So you do certainly encounter just stray microwaves basically at your
Yes.
addressing frequency.
think at some point we went on a big cleaning up microwave hygiene mission and things got a lot better. But you know, when we do spectroscopy scans, we see the 0 to 1 transition, the 1 to 2 transition, and the 2 photon transition from 0 to 2. It's much smaller, one state population, but it's definitely there. And the sloppier you are with filtering the microwave lines, the more problems you have. Yeah, but it's not always an easy thing to thermalize to the base plate of your dill fridge. You can get the components that you can buy are getting better and better and better, actually. So it's becoming easier and easier. All right, Andrew.
I want to try to answer your question.
I think then maybe we really need to throw the cube.
So simply, I think power of resonance regime, we call it dispersive regime, with light scatter ensemble. So the power of resonance, basically, the main hit from the light is the vision, whereas if you're closer to resonance, or you get light scattering everywhere, scatter the light. So I think that's why we always call this out, checking the dispersive regime.
All right. Okay, so then let's start talking about, oh, do I only have 10 minutes left? How many, half an hour left-ish? Okay, perfect. Okay, so now I want to talk about how we build quantum simulators out of this stuff. Okay, and so there's a few different ways that you can go about and that people have gone about building quantum simulators in superconducting circuits. One way is you just build the same thing you would build for a digital quantum computer, turn on the tones that you would normally use for gates, use all of the readout that you would normally have. So that's sort of the most obvious, but also the most digital of the quantum simulators. And so what I want to talk about more today is the slightly wackier architectures where you try to do something other than first build a full digital quantum computer and then use it for analog. And so one thing that people have done quite a bit is you could make a qubit array directly. And so this is not necessarily building a full 2D quantum computer, but you're making something like a lattice system where the qubit is a site. So in the sort of traditional digital quantum computing architecture, the qubit is a spin. You have a bunch of spins, you hook them together with some interaction, and you make a spin model. And so the idea here would be that you say your qubit is not a magnet, your qubit is a particle in some box. And then you try to hook those up in some fun way. And so you can play with the dimension, right? So you can do 1D or 2D, and you can play with the coupling scheme. So that's sort of one type of option. Another type of option is that you play with the cavity side. So you build something with a qubit in a cavity, but then you use some unusual geometry of cavity, something multimode, or different packings and things. Hopefully I'll get to talk about this a little bit at the end. I want to spend most of my time talking about this. And so this is kind of my particle is a moving boson, as opposed to my particle is a little mini magnet, sort of point of view. And so what I'm hoping to do is sort of show you one of the early devices that was made along these lines, sort of break down how it was made and why it was made. And so this was done in the group of Dave Schuster with a lot of collaboration with the group of John Simon. And so it was a 1D chain of transmons. And they wanted to observe Mott insulator physics. And so the Mott insulator is a phase of condensed matter where the repulsion between electrons causes exactly one electron to sit on each site. And given the size of the room, I'm going to draw a much bigger diagram. Okay, and so now I want to walk through what they had and why they had it. And so at the core of the device was a chain of transmon qubits. And they used these X-style transmons, which I will explain in a minute. And so these are so-called X-mon qubits. We superconducting circuits people are really bad at generating new mon names for absolutely everything. So these are X-mon qubits. I'll explain what those are. They have a direct capacitive coupling. Each qubit has a dedicated flux bias line. And so these are used to apply a different magnetic field to every qubit. You tune the flux tunable Josephson junction, the squid loop, and so then by applying these flux biases, you can make this chain of qubits actually degenerate. And they had 8 of these guys. And then in addition, so the qubits themselves were the main simulator, but they wanted a way to read it out. And so they put a readout resonator on every single qubit. So let's talk about why this looks this way, what's cool about it, what's annoying about it. So one of the most annoying things in superconducting circuits is that Josephson junctions are exponentially sensitive to the insulator thickness. So you make a superconductor, a layer of insulator, and the next superconductor, and your EJ depends exponentially on the thickness of that insulating layer. So the corollary to that is disorder. It's essentially impossible to make, 10, 20 Josephson junctions or even 2 Josephson junctions that have exactly the same EJ. You make them the same area, you run them through the same recipe, and they aren't exactly the same. And so this is the reality of life in this regime. Welcome to solid state. The great strength of the atomic qubits is every single one of them is exactly the same. The strength of the solid state qubits is they're man-made, so you can make them whatever you want, but they never turn out the same way twice. So you're gonna have to pick your poison. And so this is why they use flux bias to compensate. And so you try to make all of the qubits the same, they don't turn out the same, and so then you have to individually tune the flux on each one to make them the same. And so you can do this, but it has a cost. So you need a whole bunch of control lines. And if you make your Josephson junction flux tunable, then it's sensitive to any other sources of flux besides you. And so you have control lines, and anything that's flux tunable then becomes sensitive to drift. And so when you're designing a superconducting qubit architecture, you're sort of always trying to trade off these two issues. Can I live with the different Josephson junctions, or do I need to tune them exactly the same? What's the minimum number of tuning knobs that I can get away with? You know, how many $1,000 of power supplies and how many servos do I actually want to have? And so that's what all these flux bias lines are for. And so for an 8-qubit device, there are 8 individual flux bias lines. So it's 8 DC voltages going into this device to control the qubits and make them degenerate. Okay, and then the next part that's confusing is the shape of the transmon. So previously, I drew transmons that looked like this. So these two pieces of metal form the capacitor. And then there was the Josephson junction or the squid loop in the middle. And this is sort of the original type of design that there was for a transmon, 2 separate pieces of metal with the Josephson junction in between. This was a sort of Sholkov group at Yale style, and you'll see this style of transmon a lot in IBM. But that's not the geometry that's shown there, so that the XMON looks like this. And so the XMON has a squid loop at the bottom like this, and this is the capacitor. And you're going to look at me and you go, Alicia, what are you talking about? It's one piece of metal. It's not a capacitor. And so the answer is that the rest of the capacitor is actually the ground plane. And so the XMON lives by the capacitance between this piece and ground, and then the Josephson junctions, or the squid, connect that one floating piece of metal to the ground plane. XMON is sort of John Martinez Google style. And the nice thing about XMON is it has tentacles. And you can use the different arms for different things. And so, like, if you have a 2-qubit XMON device, like this, so this end is the flux bias end. That's where I thread magnetic field. That's where I control the frequency. If I want these qubits to interact strongly, then I can bring these two very close together with a big area. And so by changing the shape over here, I control the capacitive coupling. And then the shape over here is going to control the resonator coupling. So if I want this capacitance to be small and that capacitance to be big, I just change what goes on at this end versus that end. And there's still an extra arm for microwave drive. To come in like so. And so that's kind of the nice thing about the XMON. But one thing that I should warn you about is that this device is well sub-wavelength. And so we live not in the world of parallel plate capacitors, but in the world of fringe capacitance. And so you will usually find that there's a non-negligible capacitance from, say, over here to over here. And so it looks very separated, that this arm is for this, and that arm is for that, and that arm is for that. But it ends up being a more tangled mess. And so you have to be careful with finite element simulations if you're actually going to do this. Okay. But it's a very common shape and it definitely has its uses. All right, and so now coming back to this device, they want to make a mod insulator. And so to make a mod insulator, you need qubits that are coupled together, and you need to have an interaction. And so the energy levels of the transmon look like this. So 0, 1, 2. And so you can think of this energy difference here as being an interaction energy between photons. You put one photon into this transmon and it's at 5 gigahertz. To put the next photon in, you need to go in at 4.8. And so you can actually think of the transmon as being a fake electron with a strong attractive interaction. It's a box for electrons with a strong attractive interaction. So you have attractive interactions between photons. So that's sort of a weird part of these qubit-based sort of lattice machines. Okay, and so now the other thing that you need to do to have a mod insulator is you need to have particles in your lattice. So you can think of this as a 1D chain of sites. And if there's one fake electron on the site, it's at 5 gigahertz, 2 is at a different frequency. But these are photons, particle number is not conserved, and there's not a chemical potential. So if you just leave this thing alone and you say, please run a computation, it will happily find the vacuum for you. Right? I can be empty, that's good. So you need a way to fill this thing. And one of the key things that Dave Schuster and John Simon figured out was how to fill this in a sensible way. Because one thing that you could imagine doing for this is you do a pi pulse on all the qubits, you excite them all, and then you run dynamics, and you kind of hope for the best and hope that you can do your computation before everything all drains out. And they figured out a way to actually sort of pretty deterministically keep refilling this with exactly one photon. And so now why is that hard? So if I have a qubit in the ground state and I want to put a photon in, I say, okay, that's fine. I apply a pi pulse. And if it empties, I want to apply another pi pulse. So, but if it's not empty and I apply another pi pulse, I emptied it. And so if you just keep applying pi pulses, you'll put a photon in, you'll take a photon out, you put a photon in, you take a photon out. And it doesn't sort of pile up in the right place. And so they figured out a way to continuously drive a transmon to sort of keep it populated in this one state without having to do active measurement, error correction, and feedback. And it uses some neat tricks of dissipation engineering. And so that's the last thing that I want to show you guys, I think, before I run out of time. So the goal is to take a qubit that's sitting there and try to drive it to populate this one excitation state. So you have one excitation, not 2, not 0, without actively checking what you're doing and whether it has emptied out. So let's do a first try. I'm an atomic physicist. I know what optical pumping is. This seems like a really good idea. And so what you could imagine trying to do, actually, let me just draw this really big. So you could imagine, let's drive an excitation from the 0 state to the 2 state. The 2 state will decay to the 1 state. And then if it decays from 1 back to 0, we'll pump it back up to 2. That sounds great, except that this matrix element in the transmon doesn't exist. So you can't get to the 2 state without going to the 1 state. So plan A, nope. All right. So plan B, the 2 state is not exactly twice the 1 state. So you could apply a drive that's slightly lower frequency than the 1 state, where 2 photons in the drive takes you exactly to the 2 state, and then you sort of springboard off the 1 state, you get up there and you decay back down. And so this looks great, except if you look at the decay rates, so there are now 2 decay rates in this problem. Gamma 2, 1, the decay rate from 1 to 2, and gamma 1, 0, the decay rate from 1 to 0. And unfortunately, gamma 2, 1 is pretty comparable to gamma 1, 0. It's maybe twice as large, but it's not a lot bigger. And so that means that your speed of fixing is barely faster than your speed of breaking. And so this doesn't give you a nice, it'll do it sort of, but with very crummy fidelity. It'll spend most of its time somewhere where you don't want it to be. And so here's where these 2 guys pulled a really cool trick. So this decay rate has 2 factors in it. One is an atomic matrix element, right? What's the overlap or the dipole matrix element between 1 to 2? But the other part is the photonic density of states, the number of places that this photon can go. And so what they did was they attached this cavity, this qubit, and they added a cavity at the 2-1 transition frequency coupled to this qubit. And what that does is it gives you and they use the Purcell effect to make this decay really, really, really strong. And so now in the presence of the cavity, this gamma 2, 1 can be much bigger than gamma 1, 0. And so that guy was over here, I think, and it had like a giant honking digitated capacitor out to the rest of the world. And so they made a really lossy cavity at exactly this frequency, and they used it to suck the photon out of the 2 state and leave it in the 1 state. And this is what let them have this qubit on the end, sort of always have 1 photon, and then it would give that photon to the other qubits in the chain, and it would fill that up. I think I'm not doing justice to their mod insulator paper, but one of the things that I really like about this example is it kind of showcases the tricks that you can and cannot play with a superconducting qubit. And so the normal 3-level system, Raman transition, optical pumping things that you would do in an atomic qubit don't tend to work in the superconducting qubits because the selection rules are not good. If you have a selection rule, it's the wrong one. And if you don't have a selection rule, then these tricks don't work very well. But one of the big advantages that you have are twofold. So one, there's a lot of different circuits that give you the same Hamiltonian. And so you have a huge amount of freedom to decide how to implement a circuit, depending on what you care about. Do you want to go for the double-sided transmon? Or do you want to go for the XMON? They have a different footprint. They couple differently to different things. There's also a lot of different kinds of cavity that you could use, not just the coplanar waveguide one that I drew. And so that gives you a lot of ways to optimize depending on what your biggest enemy is. And the other thing is that it's actually really easy to make narrowband filters that are narrow compared to the frequency spacings and all of these other things. And so it would be, I think, it would be very challenging to use a Purcell effect in an atomic system to really accelerate decay at a very specific frequency. But it's quite easy in the microwave, and you can really make these narrow resonant filters. And so, so I think I'm just to the end of my time. And so what does that mean? All right, I'll skip talking about my stuff, but I think the big advantages of the superconducting circuit platform is it's very, very flexible in how you implement things. You can choose your frequency scales, you can choose your coupling scales, big or small, turn it down. You can choose how it's implemented on the chip. So that gives you a lot of freedom. The price that you pay for all of that freedom is it never turns out exactly the same way twice. And also it ends up being sort of good at sort of orthogonal things to a typical atomic simulator. So if you have 8 qubits like this, the very hardest thing to do in this entire device is to flip all of them at once, the exact same amount, or to detune all of them at once, the exact same amount. Things that would be very naturally done, you shine a laser on all of your atoms or your ions and they flip. You change your bias magnetic field and everything changes. But here you have lots of fringe fields, inhomogeneous offset fields. And so what's much more natural here is to have a few local control knobs and very strong coupling, and then play with it from there. A lot of what I do is actually playing with the shape of the cavity, and you can do some pretty interesting connectivities if you choose your cavity geometry correctly. But I've run out of time to tell you guys about that. So.
Any questions?
Like when the Hamiltonian is coupled to like meaning if I was supposed to ask about like the Hamiltonian part or like the broadly and now I was coming into like those.
Yeah, so that's a somewhat detailed question about this particular implementation, but the question is, if we went and mucked with all of the dissipation over here, have I messed up my interaction? And so there's sort of, I think, two answers that I would give. Is one is that what we've really done is we've mucked with something outside of the Hilbert space that we intend to use. And so once you're in the one state, this is a little bit invisible. The other thing is that actually they only did this to the one site at the end. And so they turned this one qubit at the end into a one photon machine. And it would try to pass that photon further into the chain. So if this qubit is always refilled to 1, if that one's empty, the excitation can go over. If it's already full, then it's at the wrong energy. And so they were able to use this one site to fill the rest of the chain. And these guys did not have that extra cavity sort of messing with things.
So I have a very general question. So in the previous dimension, it was like 10 millimeter by 10 millimeter each of the qubit, and it seems like here it will be around, it can be around like 20 millimeter by 20 millimeter each of the qubit.
I believe that this chip was around 7 by 7 or 10 by 10 millimeters. I don't think it was so huge.
Okay.
But
yeah. So still, if we think about just 100 millimeter wafer, then it will be still like very low compared to if we think about spin qubits, so which are very small. So is there like any comparison that we can think of?
well, so this is an eternal argument between the superconducting and the semiconducting people. And so the semiconductor people say, my qubit is 5 nanometers in size, and so I can make 1 billion of them in one of your capacitor pedals. And then if we feel like arguing, then we answer back, but yes, one of your qubits takes 25 control lines, and the footprint for all of the DC voltages that you use to control that one qubit is A, bigger than our qubit, and B, blocking your ability to put any more next to the first one. And so and maybe so what I would say is that it is indeed a problem with these guys that they are so big, but you have to be careful to include the entire package if you're going to make a comparison like this, right? You know, an ion is an angstrom in size. The trap that holds that ion is not an angstrom in size. And so, you know, ion traps are as big as these or bigger. And so you have to be a little careful to take everything into account there. That's what I would say. But no, they are huge. That's undeniable.
Thank you.
Hello, for this Mott insulator thing, how do they know it was a Mott insulator? Is it just because it is one photon at each site, or is there like some other property that they looked at?
So they measured the occupation, and so the only thing, so the way that you can think of it is that this guy always has one photon in it, pretty much. And so it's able to give exactly one photon down the line. And then they measure the occupation of the rest of them. And there's nothing keeping two excitations from going onto the same site except the on-site energy. And so the fact that it fills to basically unit filling is showing, the fact that it doesn't go to 2 is Mott, and the fact that it doesn't go to 0 is that there's sufficient coherence time.
Thank you.